Welcome to session 12 of Dr. Donald J. Wheeler's Understanding SPC seminar. Here we consider the specialty charts created for use with certain types of count-based data. These charts are compared and contrasted with a chart for individual values, which can be used as a generalized approach in place of these specialty charts. Finally, we will look at the secrets of using count-based data effectively. This session will use the SPC workbook and Understanding SPC, where we shall begin on page 255.
Count data differ from measurement data in two ways. First of all, there's an irreducible discreteness. And secondly, every count is defined relative to some area of opportunity. And if you don't know the area of opportunity, you really don't know what you're looking at. Now, there are two basic kinds of count data. There are counts of items, and there the area of opportunity will be some finite counting number n, which defines the number of items examined when looking for the attribute. With counts of items, you can count the number of items out of n items that possess the attribute, or you can count the number of items out of n items that do not possess the attribute, like when we were counting the yellow beads. We could have counted the number of yellow beads or the number of beads that weren't yellow in each paddle of 40 beads. Count of items. The other kind of count would be a count of events. Now, a count of events, you can count the events, there are discrete events, and they occur in some area of the finite region of space or time or product. But you can't count the non-events. So you can only count the discrete events themselves. So it's a slightly different world with a count of events than with a count of items. And people get lost in all of this, and for good reason. We'll talk about that later. But the real key to opening up your possibilities is here at the bottom of page 256. There are four typical charts for count data: the NP chart, P chart, C chart, and U chart. They are all special cases of the chart for individual values. So if you want to simplify life, you can take your count data and put them on an XMR chart. If your area of opportunity is constant from time period to time period, you can put the counts on your XMR chart. If your area of opportunity is changing from time period to time period, one horrible day in Salt Lake City, I opened up my bead bowl and I had no paddle. So I grabbed coffee cups and I scooped and poured. I didn't scoop and pour the same number for every student. So we had to do an XMR chart for proportions, yellow beads. Convert the count into a rate and put the rates on a chart. That's how you handle unequal areas of opportunity. If your count data are characterized by a binomial model, then
I have questions up.
Yes, question, Henry.
Yeah, so for the area of opportunity, so should I think of constant being constant interval between
Constant
the data?
is very, very loose. The general rule of thumb here is plus or minus 30%. So it doesn't have to be really constant, just roughly constant.
Okay.
Good. So if your counts are characterized by a binomial model and your area of opportunity is roughly constant, you can put the counts on an NP chart. Or you could put the counts on an XMR chart. We'll look at that in a minute. If your area of opportunity is variable substantially, then you convert the counts into proportions and put the proportions on a P chart or put the proportions on a XMR chart. If your count of events These are counts of items. If your count of events is characterized by a Poisson model, you can count the number of hurricanes per season, but you cannot count the number of non-hurricanes, for example. And your area of opportunity is roughly constant from time period to time period. C chart for your counts, or XMR chart for your counts. Variable area of opportunity, put the rates on a U chart or put the rates on an XMR chart. Now, on page 260, what does it take to use an NP chart or a P chart? Two conditions. You need to, first of all, your counts need to be counts of items. So you can count the number yellow or the number not yellow. You can count the successes or the failures, the conforming or the non-conforming. Secondly, let P denote the probability a single item possesses the attribute. The value of P must remain constant for each of the N items in a single sample during a single time period. In order for the data to qualify for the binomial model, you've got to have a constant value of P within each time period. Now the chart will check to see if the P is the same for time period to time period, but within each time period, you got to have constant probability of an item. That means the items can't cluster together. The items possessing the attribute cannot cluster together or clump together. And also whether or not one item possesses the attribute will not affect the probability that the next item will possess the attribute. But when you have binomial counts, you can use this wonderful little equation and this beautiful mathematical simplicity. No messy constants to look up in the tables, just the elegant little formula makes people think, well, this is neat. I thought that too when I first started teaching this. Then I got into plants and realized nobody could figure out if it was binomial or not. And a lot of the data they were calling binomial wasn't.
So let's look at the difference between an XMR chart and an NP chart by turning to pages 60 and 61 of the SPC workbook. On page 60, you have 8 sets of 25 counts. These are the numbers of yellow beads drawn from the bead box for each of 8 classes. The charts on page 61 show the X chart for each set of counts superimposed on the MP chart for that same set of data. Here we have the sets A and B. Of course, the X chart and the NP chart have the same running records since they are showing the same data. Moreover, the X chart and the NP chart have the same central lines, even though the computations look different. So the only difference between an X chart and an NP chart is how they compute the 3 sigma distance for the limits. The X chart computes an empirical 3 sigma distance based on the variation actually present in the data as measured by the moving ranges. These are the limits shown as dashed lines. The NP chart computes a theoretical 3 sigma distance based solely upon the average count. These are the limits shown as solid lines. When the theory is right, as it is in this case, the empirical and theoretical values will converge, and both charts will tell the same story. Here, there is no practical difference between the 8 pairs of limits. The empirical limits have 1 false alarm out of 200 points, and the theoretical limits have 2 false alarms out of 200 points. But what can happen when the theory is wrong? For an example of this, let's turn to page 270 of Understanding SPC.
Here are percentage premium freight shipments on a P chart. Looks like it's pretty out of control, right? But look at the numbers here. Look at the N. These are the number of shipments coming into an assembly plant each month, and they're in the thousands. And anytime your area of opportunity is in the thousands, I'll guarantee you P is not remaining the same for all of those thousands of items. You're never going to satisfy the binomial condition when N, the area of opportunity, is up in the thousands. Just isn't going to happen. So let's go back now to page 258, same data. And this is what the same data look like on an XMR chart. Because these data did not satisfy the binomial condition, the theoretical limits on page 270 are wrong. And they're not just a little wrong, they're a lot wrong, you see. They can blow the limits up, they can shrink the limits down, all kinds of errors can happen here. But when you put it on an XMR chart, you can see what's really happening because it's totally empirical. It lets the data speak for themselves in terms of how much variation is going on. We don't assume we know, we listen to the process. On the next page, additional data is plotted. You can see there was a change in the use of premium freight. That's the change you want to know about, not the spurious signals on page 270, the real change on page 259. There's only one caveat, and that's the caveat of chunky data, page 259. As long as your average count exceeds 1, page 259 in Understanding SPC. As long as your average count exceeds 1, you won't have chunky data with your count data. When your average count starts falling down below 1 per time period, you're going to start to run into chunky data problems. But when your average count falls below 1, you have a very rare event or a very rare count. And your count data are going to become very insensitive. And you need to shift from counting the rare events or rare items to tracking the area of opportunity between the rare events or between the rare items, like I explained on page 100 of Understanding Variation. So that's the only caveat, and it's the caveat of chunky data. So how do you choose a chart? Page 280. Here's a flow chart for choosing a chart. Here's an average and range chart. Here's an XMR chart. And there are 5 diamonds you have to go through before you get to an NPPCRU chart. If N is larger than 1,000, just forget about it. Go use an XMR chart. Is P constant within each sample? No. Organize data in rational manner, put it on an XMR chart. Is N constant from sample to sample? Yes. May use an NP chart. No. May use a P chart. Down here, the steps to go through to get to a U chart and a C chart. And along the way, I give you a don't know option. And if you don't know option, it takes you back down here to the XMR chart. Or you can just forget the whole chart and just use an XMR chart for individual values and an average and range chart when you're dealing with subgroup data. Makes the whole life simpler.
But sorry, I don't understand why you would choose to use a P or NP or U chart, because you take the risk that it's not homogeneous, the data. Why would you do it? Do that?
Okay. If you qualify, if you do have data that seem to qualify as binomial or Poisson, same kind of problem, I just haven't talked about it. It's in the book. If you qualify, the limits you get from the NP chart or the P chart or C chart or U chart stabilize more quickly. They have more degrees of freedom. That's the only advantage.
But isn't that only true when you're playing with beats?
You gotta be happy that you're dealing with a binomial or Poisson variable before that advantage is an advantage. And so sometimes, yeah. Other times, no.
It's more helpful where you haven't got much data, isn't it? Because of the stabilizing quicker thing.
Yeah, but you still have to qualify as binomial or Poisson, otherwise just go ahead and use
otherwise you're in the wrong place. But if you've only got a few data points, then you might get a tiny advantage.
You only got 2 data points.
Well, not 2, a few. I said a few, not 2.
Okay. Just for your information,
convert.
You cannot, with 4 data points, you cannot get a point outside the limits in the baseline. The arithmetic won't allow it. 5, it's almost impossible. Before you can get the first or last point out, you have to have at least 6 data. And before you can get an internal point out, you have to have 8 data on an XMR chart. So 6 to 8 data is kind of minimum we like to see. I have occasionally done it with fewer. You have examples in understanding variation where all we had was 4 data. So we used the 4 data. And we can't internally compare it, but we can compare it externally to other data. And that made sense. So, yeah, I've had people just say, forget chapter 10. Use the XMR chart. It's the Swiss Army knife of control charts. You see, it's not the way you chart the data, it's the way you organize the data that counts. With count data, we tend to aggregate the data up to a high level, and that gets to be a problem. And so quite often the secret with using count data is disaggregate. Break it down, and we'll show you examples of that.
Now we turn to Chapter 11 of Understanding SPC, which reveals the secrets of using count data effectively by means of several different examples. We begin on page 285.
There are 3 characteristics of count data that make it difficult to use count data effectively. 1, page 285, we count bad things. So the better we get, the harder it is to find something to count. I actually had a student write me, say, we count the number of downed cows in the feedlot each day. The average is less than 1. I guess that's good for the cows, but it's bad for the chart. You had rare events, you see. So we're counting bad things, and so the better we get, the fewer bad things we have to count. The second thing is we tend to use count data when we could measure something. And count data are not a substitute for measurements. There's a picture here on the screen, it's on page 286. These three distributions all have 16% non-conforming. So they would all look the same to a P chart, but they certainly wouldn't look the same to an XMR chart or an average and range chart. And the third common characteristic of count data is that variation coming from separate sources is difficult to identify. We aggregate our counts up to a high-level report card statistic, and then we have trouble interpreting that statistic. Case in point, page 288. Number of rejected parts per basket. These are steering wheels. A basket of steering wheels contains 60 steering wheels. So where they made the steering wheels, a clerk from the quality control department went out there once a day, and for 60 consecutive pieces coming off the line, he kept track of the reason for rejection. There were 3 inspectors, and when he showed up, they'd tell him why they were rejecting any wheel they rejected. He'd record the reason for rejection, and then he'd total them up and created the chart you have there on page 288. And there's a point below the lower limit. There's a point way above the upper limit. We've got a long run near the limit here. There are some signals in these data. But you see, this is a report card metric. So this is a report card chart. And report card charts aggregate everything together, and that tends to hide the signals. I said, while you're tracking these, you need to have a chart for each category. And he said, well, we have a running record for each category, and pull the charts out on the next page. And I said, well, this is where you need your limits. So I put limits. This is just an NP chart formula, real simple. Limits on farm material, they're 3 points out. Limits on damaged edge, and they're 2 points out. I didn't bother to put limits on sinks because they're onesie-twosie. Damaged mount, 5 out. 2 out for stress, 2 out for bubbles, 1 out for other. This is the chart on page 288 with all of the signals from page 289 marked. I mean, does the chart on page 288 look like you have 14 out of 21 points out of control? That's what report card metrics do. When you aggregate the data up, the aggregation accumulates the noise, and the noise obscures the signals. So the secret to using count data effectively is disaggregation. Break it down. So the same part number we're talking about on page 288 and 289. On page 291, you have the data from 6 months later. same part number, but 6 months later, how many reasons for rejection do they have? Instead of 8, they have 16. How do you go from 8 reasons for rejection to 16 in 6 months' time? Well, I asked them and they said, because we have more categories because we think we have different assignable causes. See, that's the secret. You've got to get the category narrowed down to the point that you can determine what's happening in production. See, foreign material up here used to include lint and vapor drip. Vapor drip is completely different than lint, is completely different than foreign material in the resin. 3 different problems. Earlier, they were called foreign material. That spike on page 288 was for foreign material. I happen to know that that spike was vapor drip, but you couldn't see it was vapor drip on page 288. Here you'd be able to tell that. And let's look at lint. Lint is not a mystery when everybody wears cotton gloves, right? If everybody's wearing cotton gloves, this should be a no-brainer. But look at the data. 1, 16, 0, 2, 1, 0, 0, 0, 2, 0, 10, 5, 1, 1, 0, 1, 1, 2, 0, 1. On page 292, or well, here's the page 292 is the running record for lint. Andy noticed that he got a lot of lint when his 60-piece audit included a lot of rework. And rework consisted of taking an acetone-soaked pencil and rubbing it down. So they started using organdy cloth on re-op. Yep, all the lint was coming from the cheesecloth, not the cotton gloves. Well, they couldn't fix the problem until they could identify it. Now, once they started using organdy, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and Andy told me, I made sure each of those audits included reworked wheels. You can't turn it off until you can identify it. You can't identify it as long as it's just foreign material in general. You see, it's the disaggregation that makes the counts effective. Now, they were averaging 22 rejects per 60 wheels back on page 288. So about 1/3 of their output went to rework, and about 2/3 of their output went to the assembly plant. Now, they were going below the lower limit and here in early, so they recalculated the limits halfway through the month and still went below the lower limit. Unheard of levels of quality. One of the things they did was take the chart out of the quality department and started posting it on the wall in the steering wheel department so people could see what was happening. Now, what about this spike at the end? It's all bad insert trim. And it's real simple. Somebody had the bright idea. These steering wheels had a little insert piece, a trim piece put in. And the insert piece was put in by the worker and then cut off with a razor blade, just a single-edged razor blade. And somebody had the bright idea they could save a penny by not giving everybody 2 blades. Gave each worker 1 blade each shift. And so they couldn't get away to go get another blade. They had to keep the line running. And so this spike is bad insert trim from dull razor blades because somebody had the idea to save a penny by not giving them access to more than 1 razor blade per shift per worker. Dumb idea.
Our next example comes from David Chambers, the co-author of the textbook and my mentor. A medium-sized hosiery mill employing about 1,500 workers had the reputation of being a quality mill. This was based on careful 100% inspection that graded the output of the plant into 4 categories. First, irregulars, seconds, and rags. In spite of this reputation, the mill faced a real problem. Since the workers were paid by the piece, each one had to process a certain number of pieces per week in order to earn the minimum wage. Facing an increase in the minimum wage, the managers realized that some way had to be found to increase the income in spite of the soft market and stiff competition. And one way to do that would be to reduce the number of irregulars, seconds, and rags. So to this end, the president sent 20 supervisors to attend an SPC class at the university that happened to have been taught by David Chambers. After the class, Professor Chambers sat down with the supervisors and helped them to plan how to use SPC in the plant. Due to the nature of the work, they decided to begin in the looping department. Now, the looping operation closed the toe of a knitted stocking. It was a tedious operation, requiring the operator to thread the toe of the stocking onto a comb-like device called the looper dial. Exactly 1 thread from each side of the stocking had to go onto each gap between the teeth on the looper dial. A missed gap would create a hole in the finished stocking, resulting in a downgraded stocking. Placing 2 threads from the same side in 1 gap would create a pucker, resulting in a downgraded stocking. After the stocking was threaded onto the dial, the end was trimmed. If it was trimmed too long, the seam would be bulky, resulting in a downgraded stocking. If it was trimmed too short, the stocking would fall off the dial, and the operator would have to start all over again, which is bad form when you are being paid by the piece. After being trimmed, the toe of the stocking was stitched by the looping machine, and the finished stocking was automatically ejected into the looper's production box. To collect some data, an inspector was brought into looping from the inspect and pack room. The inspector went around the looping floor 4 times each day, using a different order each day. At each stop, she would inspect 4 stockings. Thus, she obtained a total of 16 stockings from each operator each day. During the baseline period of June and July, the departmental average was 4.8% defective at looping. This report card chart shows the looping department, if left unchanged, should be expected to create about 5% defective. But the report card chart does not tell us how to reduce this defect rate. Since the loopers operated independently of each other, the supervisor had to identify which operators needed help. Accordingly, the data from June and July were used to create an NP chart for each worker. The central line of 0.8 and the upper limit of 3.4 were based on the departmental average of 4.8% defective and the daily sample of 16 pieces. Beginning in August, the supervisor sat down with each operator and showed them their personal chart. The operators were told that if their work was average, they should have between 1 and 3 defectives. 4 or more would be worse than average, and 0, that's better than average. Now, operator 75 was one of the best operators in the department. So the supervisor went out to watch her work. And when he did, he noticed that she was using a different technique from the one that was taught in the training room. So the supervisor got operator 75 to start teaching her technique to others. Operator 22 was much worse than average in July. After observing her at work, the supervisor had her referred for a possible eye examination. It turned out she was blind in one eye and only had 6/20 vision in the other eye. However, glasses got her back to 20/20 in that eye, and her work immediately improved. It ought to. She could do this job blind. With her improved quality, she got a 15% increase in pay and became a gold star looper in September. After these improvements, suddenly all the other loopers were getting new glasses. Operator 27 seemed to be the least capable operator during the baseline period. When the supervisor discussed her chart with her and explained the quality improvement program, her response was, "Why, I've been here for 5 years, and this is the first time anybody has told me they were interested in good quality. I can do a much better job if it makes any difference." And she really could. The record for operator 106 deteriorated between June and July. Examination of her personnel file revealed that she had been moved from the training room to the production line in June. Beginning in July, she was pressured to increase her output in order to minimize the makeup pay. In response to this pressure, she was working faster, but her number of defective stockings also went up. As the supervisor watched operator 106 work, he noticed that she had a limited mobility in her right arm. This impairment made it difficult for her to load stockings on the looping dial, slowing her down. The supervisor got operator 106 a handicap certificate, which allowed her to produce a higher percentage of good pieces while working at her own pace. And operator 73 was a lady in her early 60s who had been looping for 10 years. During June and July, her production had either been worse than average are perfect. Worse than average are perfect. Worse than average are perfect. And then back to worse than average as the inspector kept coming around, pressure was beginning to build. Nothing in between. The supervisor worked with her during August and thought he saw some improvement. In September, she decided that new glasses might help, but the chart shows no evidence of improvement. By October, it was apparent operator 73 had improved as much as as possible. When compared to the other operators during the same time period, her work was indeed poor. Although the supervisor did not think that she could do any other job in the plant. He was reluctant to terminate a 10-year employee. He decided to give her more time. During November, Operator 73 produced 20% of the non-first grade material produced by the whole department. By that time, the other 49 operators in the looping department knew that Operator 73 was holding the whole department back. As group pressure increased, the supervisor finally realized that something had to be done. The managers reluctantly agreed to let Operator 73 go at the end of the year. At the company Christmas party, it turned out that Operator 73 won the first prize, an expensive electric range, in a random drawing. Near the end of the year, she was informed that arrangements for a suitable pension had been made. When hearing this, Operator 73 was neither surprised nor dismayed. She said, in fact, that she had known for 10 years that she could not loop well and could not learn how. She didn't think she could. The chart shows this mental block during the baseline period, where she was either worse than average or perfect. As long as she didn't think about what she was doing, her fingers could do the job. So Operator 73 left with a good attitude, realizing that the supervisor had done everything possible to help her improve her performance. Well, how'd they do? The overall record of the looping department was one of continual improvement. The first month, the percentage dropped and effective pieces dropped from 4.8% to 2.4%. The following months, it rarely rose above 2%. By February, it was down to an average of 0.8%. This is an 83% reduction in the number of defective pieces produced, and this reduction was accomplished in a period of 7 months.
And finally, robots. Robotic assembly operation. These robots put the pal nuts on plastic studs to hold the handle onto the door trim panel. So the cart comes along the line. Here, a camera takes a picture of the part to locate where the studs are, and then communicates to the robots. And each robot is supposed to put on 4 pal nuts. And of course, there's a safety cage around the robots. And so you watch it, and the arm comes out, and the arm comes up, and the nut slides down the face and falls off. These robots had specially been modified, like any robots I've never seen before or since. They had diapers to catch the nuts that fell off the panel. 70% ended up on the part, 30% ended up in the diapers, and they were there to keep the area clean. They could clean up more easily. Robots with diapers. That's really the way to do it. So over here against the paint booth, well, there's not much room to work. Two men whose job it is to put pal nuts on mangled plastic studs. After the robot finishes, sometimes there's not much left. So collect some data. We decide to watch Robot 7L, collect data on Robot 7L while we're making one particular part number. There's I think six part numbers coming down this line. So we did this with a data collection sheet. Robot 7L, panel A, what time, what day. Whenever a cart number 1 comes by, you put a tick mark here, and that's 4 attempted installations. Then, if one of them is a miss, you put down mark the reason for rejection. There's 7 reasons for rejection you can spot standing outside the cage. Drop nut, nut upside down, jam in the feed tube, jam at the head, so on. So that's 1 missed out of 4. That's 2 missed out of 4. Here was 4 successful applications. The quality director, after we collected the data, said, I'm convinced it's the carts. The carts are just not stopping in the right place. I said, let's find out. Compute a percentage missed for each cart. No detectable difference. Wasn't the carts. Here are the data for panel A. Each dot is one of these sheets. Each sheet takes about 10 minutes to fill out. All 30 carts come by in 10 minutes. So you fill out one sheet of paper, get another piece of paper. So each of these, what have we done here? With the data collection device, we have preserved the context for each event. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 successive misses. Jam and feed tube is what that's going to be. So we can see what's happening with the data structure on the data collection sheet. In fact, the plant manager told us she had 12 skilled tradesmen working full time to keep these 6 robots up and running. Now that's the highest pay category in the plant. Well, the tradesmen, the skilled workers, were looking over the shoulder of the data clerk and were fixing the problems that they could see on the data sheet. And while they were collecting this data in 2 weeks' time, they went from 70% installed to 94% installed, because it was a matter of maintenance. They hadn't figured out how to maintain the robots yet. Each dot here is 1 sheet of paper, which is what, 10 minutes elapsed time? And some of these are consecutive. So 4.3 tells you the process is capable of virtually perfect operation. And all the other days show you they don't know how to maintain the robots. I mean, one of the problems is drop nuts. The nut would drop off before it got to the part. Well, they weren't cleaning out the filter on the vacuum system except once a week. Now, these robots are in a trim plant. They're cutting velvet with saws not 50 feet away from these robots. A trim plant is almost like a textile mill. The air is white with lint. Lint is not a friend to robots. They figured out drop nuts was one of the causes they were dealing with. They started cleaning out the vacuum filter every day, and drop nuts went away. While they were collecting data on the whole system before, they weren't dealing with one robot in one part number. They had 6 different part numbers, 6 different robots. And so they had all these different combinations that they were dealing with, and the data were just lumped together into one big aggregate. And they couldn't tell anything except, ain't it awful? And we got 70% installed. Report cards are useful if you want to know the overall level of defectives, but report cards don't tell you what to fix. When you have report card metrics, whether it's measurements or counts, the secret is disaggregate. Break it down when you get down to the point where the activity is actually taking place. So you know what's happening, and that's where you're going to discover what it is that needs to be fixed. One last story, and this is on measurement. Figure 1119. Percentage failing under performance load. These are motor mounts. This is the percentage of motor mounts that fail under performance load. And winter and fall are your best seasons. In spring and summer, the percentage just skyrockets. And the director of engineering sat down and told me all the things they tried to fix with no success. They figured they're going to have to live with this. You see, in summer and spring, the humidity levels are higher, and the adhesive is hygroscopic. And that absorption of humidity makes the sandwich between the rubber and the metal weaker. And they just figured they had to live with this. Then, the spring of '82, 2.5%, I'm sorry, 3%. They hadn't been down to 3% ever. Summer came, they were down 2.5% or so. It kept going down. The general manager said, "What did you find? What have we been missing for 6 years?" I said, "We don't know. We're doing everything the same. Tell us more about that next week." So they came back to the meeting next week and, okay, we're doing the same thing we've always done, but we have 16 charts out there. And every one of the charts shows reduced variation. And when we reduce the variation on each of the steps, suddenly everything is running closer to the target and our quality level is improving. Variation creates cost, and it hurts quality. It can do no other. And the only way to consistently reduce the variation is find the assignable causes of exceptional variation and get rid of them. Make them part of the set of control factors, or learn how to compensate for them. Until you do that, you're going to continue to operate in the cycle of despair. Well, that's the secret of using count data effectively. It's not what type of chart you use. I've used a lot of NP charts in this chapter, if you notice. It's the disaggregation. It's the rational organization. It's understanding how to listen to the voice of your process and react to the signals that you find. Aristotle taught us the time to discover what causes affect your system is to study those points where the system changes. And the process behavior chart is a systematic way to do just that.